Now we'll turn deployed smart contracts into real application behavior. With Web3.js or Ethers.js, your client connects to Besu through JSON-RPC, reads contract state, sends signed transactions, handles receipts, and responds when blockchain events occur. You already have the core layers in place: what Besu is for, how enterprise networks are designed, and how smart contracts are deployed. The next step is integration. We'll connect an application to Besu so users can read data and interact with contracts. Besu acts as the gateway between application code and blockchain state. Your front-end or back-end uses Web3.js or Ethers.js to turn familiar method calls into JSON-RPC requests over HTTP, WebSocket, or IPC. Read-only calls can use a call. State changes are signed by an account, sent as transactions, and checked later with receipts. Contract ABIs provide the encoding map so the app knows how to call functions and interpret results. JSON-RPC is the language your application uses to talk to Besu, and a provider is the client-side connector that speaks it for you. Use HTTP for normal request-response work, like reading state or submitting a transaction. Use WebSockets when the app needs live subscriptions, such as new blocks or contract events. Besu must expose the right APIs, including ETH/NET and WEB3, and enterprise networks often add firewall or gateway controls. When building against Besu, Web3.js and Ethers.js are both valid choices because Besu exposes Ethereum JSON-RPC. Web3.js is often attractive for teams with older Ethereum codebases or developers who already know its patterns. Ethers.js tends to feel cleaner for newer apps with strong provider, signer, and contract abstractions. Choose based on your framework, bundle constraints, documentation preference, and team familiarity, not Besu compatibility alone. Before writing contract integration code, confirm that your Besu node is online and exposing the JSON-RPC endpoint you expect. The provider is the application's bridge to that endpoint, whether you create it with Ethers.js or Web3.js. Once connected, run a quick sanity check. Read the chain ID, latest block, or client version. Those values confirm you are on the right network before querying state or preparing contract calls. The provider is your phone line to the blockchain. It lets your application read data and submit messages, but it cannot approve anything by itself. A signer, or wallet, is the authorized identity holding the secure signature. Any state change needs that signature, plus enough native currency to pay gas. In development, local test accounts are fine. In production, never hardcode private keys. Use a vault, HSM, or managed signing service instead. A contract object connects your app to a specific deployed contract. The address tells the app which contract to talk to, and that address changes by network. The ABI tells the app what the contract understands: function names, inputs, return values, and events. Libraries like Web3.js or Ethers.js combine both pieces. If either one is wrong, the app may connect to nothing, or call the contract incorrectly. When an app needs contract data, it usually makes a view call, such as contract, get value in Ethers, or call in Web3. Under the hood, that becomes an eth call request. Nothing is mined, no transaction is created, and the user pays no gas. The result comes back ABI encoded, and the library decodes it. Application code should then format it clearly, converting bigint values into token decimals or display strings. For dashboards, avoid excessive polling. Contract data should not be treated as ordinary app data. Solidity integers can exceed JavaScript's safe range, so keep them as bigint or the library's native type. Validate and checksum addresses before showing or storing them. Convert token units deliberately because WE and Ether are not interchangeable. When contracts return tuples or structs, map them into named domain objects. That small translation layer prevents confusing displays and subtle business logic bugs. Updating contract state starts with the application, building a transaction from the contract ABI, the target function, and its inputs. That transaction must be signed by an authorized account, either locally or through a signing service. The signed payload is submitted to Besu commonly with eth/send-raw transaction. Besu validates it, shares it with peers, and includes it through consensus. The application then tracks the transaction hash and waits for eth get transaction receipt, plus any required confirmations. A transaction hash only proves the network accepted the submission. It does not prove the state changed. To know the outcome, inspect the receipt, status, gas used, logs, and block details. If execution failed, look for signals like a revert, low gas, nonce conflict, invalid input, or access denial. Then wait for enough confirmations before treating success as final. Good applications translate this into clear user states: pending, confirmed, failed, reverted, or timed out. Instead of constantly polling contracts, applications can react when something meaningful happens. A solidity event is emitted during transaction execution, and Besu records it in the transaction log. Listeners or indexers can query past logs or subscribe to new ones over WebSockets. Good event design includes indexed fields so consumers can filter efficiently and trigger notifications, API updates, automated workflows, or audit checks. A useful Besu app rarely does just one thing. It reads state to initialize the experience, check balances, or load contract values. It writes transactions when a user approves, transfers, or updates something. Then it listens for receipts and events, so the application reacts only to confirmed results. Keep configuration, provider setup, contract services, and UI or API code separated. That separation makes the workflow easier to test, monitor, and evolve. You've now connected deployed Besu contracts to real applications. Providers reach the network, ABIs shape contract access, calls read data, sign transactions change state, receipts confirm outcomes, and events drive responsive workflows. Next, we move from mechanics to enterprise design: maintainability, upgradability, governance, security, and compliance.